Okay, good morning, everybody. Let me just check the voice and video. Are you getting proper voice and video?
Yes, sir.
Okay, so let's get started. Uh, we were looking at the hardware for the ALU design, hardware design for the arithmetic unit. And soon we'll look at the details of the hardware of the processor. We had seen multiplication, the standard way of multiplication that we do normally. We wrote an algorithm in the form of a flow chart, and I asked you to write the algorithm and then the hardware implementation of that and optimization of that hardware. Now let's look at the division. The division also, the hardware design is based on the way we do binary division. And we had started to discuss this in the last class. And of course, before we start the division, we must take care of the zero division, division by zero. So this is not included in the hardware. It should be done by the software. And we were taking an example, the way we do binary division manually, and we will propose our hardware design based on this. Now let's observe this simple division example. So the dividend and we have the divisor. We write the divisor at the most significant bits. And then we try to subtract. If we are able to subtract, if this is the divisor is less than the most significant bits of the dividend, then we write 1 in the quotient. And then we perform the subtraction. And in each step, we bring down one digit, one bit from the dividend, and then try the subtraction. If the subtraction cannot be performed because the number here is less than the divisor, then we put 0 here and bring one more digit bit down. And once we are able to do the subtraction, we put a 1 here, and then we proceed this until there are no further bits to bring down. That's the way we do the typical binary division. Now here we need to do a small bit of adaptation of that, because the hardware is not efficient for some things that we can do mentally. This division is called as the long division approach, but to implement it hardware, we do a restoring division. The main reason is that in computer hardware, it's difficult to say which number is greater just by observing, analyzing the numbers. It's a bit difficult. Even though manually by observing we can do that, but here in hardware that's a bit difficult. So what we do is we carry out the subtraction, and if we get a negative number, then we restore back the number back by adding the divisor to that. While doing mentally or manually, we don't do that. Just check the number and then we don't do the subtraction. But here we actually carry out the subtraction. And then we see if the number is negative, that is the MSB is 1, and then we restore back by adding the divisor. So that's the way we do it. In hardware, that's much easier. And of course, we will, just like in the multiplication, in division also, we will do only unsigned numbers. Multiplication and divisor using unsigned numbers, because signed number is just one step extra. What we do is we check the sign of the dividend and the divisor, and based on that we adjust the sign of the result. In a multiplication, for example, if both are of the same sign, then we don't do anything. The sign remains unsigned, positive. But if they are of different sign, then we negate it. I mean, we add a negative sign. Now let's
Hello,
look
sir.
at the division hardware that we
Hello,
just
sir.
discussed. Yeah, please. Yes.
Sir, I have a doubt in the previous slide.
Yeah, please.
Sir, you have said that
So your
we
name
will
is
do.
Aman, right? Yes, sorry,
Sir,
name is Aman, right?
yes, yes, sir. Sir,
Aman,
you have
yeah.
said that the we will do division for only the unsigned bit. Then how will we check that MSB is 1 or less than how it will affect? Because in the
So
unsigned bit,
this is the one, right? You are asking that the dividend and the divisor are both unsigned.
yes, sir.
Yeah. Now, what is your question?
Then how will we check MSB is 1 or 0? Then it will be negative or positive. Because 1 is also positive, 0 is also positive in unsigned bit.
No. See here, we have the MSB as 0. If it is a negative number, we make it an unsigned number. We just negate it. Okay, so the MSB will be 0 for both the divisor and the dividend before we start the division operation. This example is just about how we do manually. So actually there is a 0 here. The MSB is 0. I think maybe the doubt is coming from there that this MSB is not 1. This is just to give an example here. We've just done this. But the way we go about doing the division is that we check if the MSB is 1, that means it's a negative number, and we negate it. We choose complement it, and we get the unsigned number, and then we proceed. Is it okay? This example, don't get
Yes, sir.
confused with
Yes.
this example. This is just for illustration. This is not an actual 2's complement number division. This is, I'll just recap the way we do manual division with a small example. But actually the MSB will be 0. Okay. So Aman, good, you asked that question. Now let's proceed. So the observation that we made there, written here in the form of a flow chart. We keep the divisor in the left half. Just see here, this is a 64-bit. We're trying to do 32-bit division. But then we have here one shift register. Here we keep the divisor in the left half. And the remainder on the right half on this 64-bit shift register. Okay, this is not a shift register, it's just a register. The remainder is on the right side. That means it is in its actual position. But here the divisor is actually shifted left. So that means it is on the left 2 bits and its value is very high. But let's see what we do with that. And the quotient is a shift register, and we have shift left on this, and this we make initially 0. And we have the control circuit here. And now let's look at the algorithm here. Once we have kept the divisor on the left 32 bits and the dividend on the right 32 bits, then we perform the subtraction. So what will be the result of the subtraction, of this subtraction? When we have the divisor on the most significant bits, most significant 32 bits, and the dividend in the lowest significant 32 bits, and we do a 64-bit subtraction. So the 32 least significant bits of the divisor is zeros, and the 32 most significant bits of the remainder are all zeros. And we perform a division. So what will be the result of this first? Sorry, we perform a subtraction. So what will be the result of this operation? Will it be positive or negative? Can anybody answer? Let me just repeat. We have a 32-bit divisor and we have a 32-bit dividend. The dividend we keep on the lowest significant 32 bits. And the divisor we keep in the most significant 32 bits. And the rest we make it zeros. And here also the least significant bits of the remainder are zeros. Now we perform a subtraction. So, and none of them are 0 basically. Okay, the dividend can be 0, but the divisor is guaranteed not to be 0. And then we perform a subtraction. So what will be the result of this subtraction? Will it be a positive number or negative number? Can anybody answer? Yes, is anybody? Okay, let me just call randomly.
Negative, sir.
Okay, let me just ask somebody else. Anusa, Anusa, are you there? Anusa, are you there?
Yes, sir.
Okay, so Aman said the first division, sorry, the first subtraction will always be negative. So can you explain why always it will be negative? The first subtraction will always be negative. I'm just asking high school stuff. I'm not asking anything deep mathematics. Rashid K, are you there? Rashid. Okay. Others, are you able to hear? Others?
Yes, sir.
Okay. So can you please explain Aman's answer that why the first subtraction will always be a negative?
So because the dividend in general should be greater than the divisor as we are dividing it from the divisor. So when we subtract the dividend from the divisor.
Actually, my question is trivial. So my question is trivial. Others, thank you. So it is always the case since we have made the divisor occupy the 32 bits, the most significant 32 bits, and the remainder, so the dividend on the lowest 32 bits here, and we perform a 64-bit subtraction, obviously it will be a negative number. And once we find that it is negative, we check here in this diamond here, we test the remainder. And if the remainder is less than 0, then we restore the original value of the dividend by adding the divisor back. But if the result is positive, then we just shift the divisor one bit right, and then we go back and again perform the subtraction. I'll just explain this with the help of another example. But this is the overall scheme that we keep on. The first one is always negative because they are in different positions. Even if the divisor is just one bit, just one, it's not 0, so it can be at most 1. I mean, at least 1. Even if it is 1 and you subtract from a number, it will always be negative. And then we shift the divisor right one bit. And when we get a negative number, what we do is we put a 0 on the quotient and we shift it left. And we shift right the divisor. So now the least significant 30 of this, the divisor has moved one bit right. And then again we perform. Now let's take an example just to make the point. Let's look at an example. And we keep on doing this for 33 iterations for a 32-bit division. Now let's look at one more example here. Okay, no, it's the same example. I'll show you with another example. So this is the same one here, just shown it in slightly larger form. Let's take another example. Okay, this is the one. So this is the red one. The is the register called as remainder. I put it red here. And we are trying to divide a 4-bit number 1100, and 1100 is on the lower 4 bits here. See, I'm just explaining with a 4-bit division. I'm not discussing a 32-bit because there are too many number bits here. I'm just explaining with a 4-bit number. So we are trying to divide 1100 by 1000. Dividend is 1100, divisor is 1000. So what we do is we put 1100 on the remainder and fill the upper 4 bits with zeros. We put the divisor on this divisor register and put the lower 4 bits as zeros. And then we perform a subtraction. Obviously, the result is negative. And then we shift. We put a 0 here on the quotient. And then we shift the divisor one bit right. I have not shown all the steps here. We again subtract from the dividend. Again got a negative number. Again restore back by performing addition. And again shift the divisor right, and so on. We keep on doing this until we are able to subtract here. 1000 has come here, and we are able to subtract, and we get the remainder 1000. So that is for a 4-bit division, we have to do this process for 5 times. For 32 bits, we need to do for 33 times. So that's the overall scheme. Now, is it okay? Or should I repeat? Okay, fine. Read up in the book also. Now, there is an example. This is the example of the book. And here, this is also an example with a 4-bit number given in the book. So here, the divisor is placed in the upper 4 bits on the divisor register. So the divisor is 0010 and the dividend is 0111 placed on the left 4 bits of the remainder register. And first time once we perform remainder minus division minus divisor, we get a negative number here. Observe the 1 here and then restore back by performing addition. And then we shift the divisor back to the right by 1 bit. So 0010 becomes 0001. And again perform the subtraction, again get a negative number. And then push the divisor 1 bit, again it became 1000 and perform the subtraction, again get a negative number. And the quotient is again push 0 there until we are able to do a proper subtraction with a positive remainder or a non-negative remainder. So 1000, once we subtract from 1111, we get a 0 on the MSB and then we push a 1 into the quotient here. And we continue for 5 times because it's a 4-bit number. So just asking this question that for 32-bit numbers, we should perform for 32 times, right? The subtraction, etc. Typically in a manual manual division, binary division, we do 32 times. So why 33 times? Okay, let me just ask somebody. Devraj Maji, are you there? Devraj?
Yes, sir.
Devraj, can you please explain that why do we have to do 33 times this subtraction operation? Because in a typical manual division, we at most do 32. So why this extra 1 here? Yes, would you like to give any answer? Vamsi Krishna, are you there? M. Vamsi Krishna, are you there? Soham Mukherjee, Soham, are you there?
Yes, sir.
Okay, so can you please explain this thing that in a typical manual division, at most we do 32 subtractions. Why 33 here in this computerized one? Computer hardware implementation, why do we do 33? Any answers, Soham?
Thinking, sir.
Okay, so please think about it. Now, anybody would like to give the answer to this? Any volunteer who will give answer to my question? So why
Sir,
third? Yes, name please.
Sankalp Srivastava, sir.
Okay, Sankalp, yes, please. Sankalp.
Sir, sir, 32 bits are for the first 0 bits that we are doing, and the last 33rd bit is for the numbers and 2 pointers at both their ends.
No, Sankalp,
First
it's not
32
that
bits all.
complicated. Sankalp. So it is not that
Yes, sir.
complicated. See, the answer lies in the first question I was asking. the first question I was asking is that why the first subtraction is always negative. So that is as good as no, we know that it will be negative, first one. So the answer is that
Okay, sir. So
they are in bit unaligned. See, they are occupying different bits. The divisor is on the most significant 32 bits, and the dividend is the lowest significant LSB 32 lowest significant bits, and therefore obviously the first one is always negative. In typical manual division, we don't do that. At least one bit is overlapping. So since we are having this extra step, just because they are in totally unaligned and it's convenient to put them into 32-bit LSB and MSB, so it will take 33 subtractions. You just check about it. You just think about it. Now let's look at the optimized divider. One important observation we need to make, just like in the multiplier, is that instead of shifting the divisor right one bit, we may as well shift the remainder left one bit. They are the same thing. Shifting the divisor right one bit, which we are doing, that is equivalent to shifting the remainder left one bit. If we can observe that, then we find that the quotient and the dividend both need to be shifted left each time. And therefore, the hardware becomes very simple. Initially, we put the dividend in the left significant 32 least significant bits. We put the divisor in a 32-bit register. We don't need a 64-digit register anymore, and we also need a 32-bit ALU. So it's much less expensive. And also, we do only shift left. Initially, and this 32-bit is doing the subtraction of this 32 MSB of the dividend. Initially, dividend is entirely on the right side here, so it is 00000 here. We're trying to subtract the divisor from 0000, and the divisor will at least be 00001, and therefore the first result will always be negative. And then slowly we shift the dividend one bit left. And then we try the subtraction again. If subtraction result is negative, we add back, and so on. So now we have simplified. We just need a shift left operation, just one operation, and the quotient is being pushed here. The same quotient which we had a separate register, as the dividend is being pushed to the left, the quotient will be added here in the bits vacated by the remainder. Very nice. Made optimal use of the hardware. Remainder is leaving places here, vacating places, and the quotient is occupying those places. And by the time the remainder is on the upper 32 bits, the quotient will be here on these 32 lower bits. They are sharing the same place. Nice. But just asking this question, that we are doing only the shift left operation. Why do we need this shift right operation here on this register? So this register, we should be able to do both shift right and shift left. And also we should be able to do the right, because each time we are writing and then we are restoring back. So why this right enable is needed, and also the shift right. I'm not doing any write operation anywhere. Just left, shift left, and so on. So can anybody answer this? Okay, it's a tough question actually. Why do we need a shift right and this right enable? And the answer lies in realizing that this is the same hardware for multiplication as well. If you look at the hardware, we finally came up, the optimized hardware for the multiplier and the optimized divider, they have the same hardware. But there we are doing shift right operation and right enable operation because sometimes we are writing, not writing, and so on. And therefore, these two extra are there, shift right and right, because we will use the same hardware for multiplication as well. Okay, from this, the hardware that we discussed where we needed two 64-bit shift register and quotient 32-bit register and perform shift left, shift right, etc. We just reduced it to a 32-bit ALU and one 32-bit divisor register here and a 64-bit remainder shift register. Now, in multiplication case, we had looked at a faster multiplier. We said by increasing the hardware complexity, by having many 32-bit adders, we could do a faster multiplication. Can we do the same thing here in faster division? Answer is no. We can do this because whether we subtract or we restore back, it depends on the sign of the remainder. There, remember in multiplication case, we observed the product bits and we could find out how to get the product bits parallelly based on the two operand. By observing the operands of by doing some operations on the operands, we could parallelly get the different bits of the product. But here we can't do that because of this conditionality of the result of the subtraction. But then some have proposed somewhat faster divider than what we discussed here, called as the SRT division technique. It's not part of our syllabus. I mean, we're not going to discuss it. We just looked at the optimized division where we optimize the hardware, but how to get the speed. It's not as fast as the first multiplication that we discussed, but somewhat fast. But then it's quite complicated, the SRT division technique. We're not going to discuss. Those who are really going to do hardware design and so on, they might later look up the SRT division, but it's not part of our discussion. But what is the instruction in MIPS assembly language to do division? We never did division in our assembly program. Okay, here also we need two registers which are implicit, the high register and the low register. Both are 32-bit. The high will store the remainder and the low will store the quotient. And the instructions are divide RSRT. And here these are the two source operands. And another one is divide unsigned. And here these instruction, before we use this instruction, we must ensure that the divisor is not 0. And once we perform the division, then the remainder and the quotient will be in the high and low register. And then we use the move from high and move from low, MFHI and MFLO instructions to access the results, the remainder and the quotient. Now let's discuss about the floating point number representation, because that's required in almost every computation that we do. How are floating point numbers represented inside a computer? Remember that for dealing with large numbers, we use this format actually. Minus 2.34 into 10 to the power 56, and 2.34 is called as the significand. 0.0022 is the significand, 10 to the power minus 4. 98702.10 to the power 9, and here 98702 is the significand. And in binary, we might write 1 point some bits, 2 to the power something. Now, this kind of representation, where before the decimal, before the decimal point, we have exactly one decimal digit. We call it as the normalized representation. And these are not normalized because there is not one significant digit there. These are not normalized, but the first one is normalized. In binary, we call a normalized representation is one where we have exactly one there, one in the left of the digit of the point here. So this we will discuss representation of the normalized binary numbers in computers, and this is defined by IEEE standard 754 in 1985. The standard was formulated, and now it is universally accepted in all computer representations. Very nice. So whatever be your number stored in whichever computer, another computer can access it. This is one case where standardization has succeeded 100%. There are many cases where standardization did not succeed. We are saying that some computers are left Indian, some computers are big Indian, little Indian, and so on. Standardization did not succeed there. But here, this is a success story. The floating point standard used universally. And we have two representation of the floating point standard. The single precision 32-bit, you might have done in C programming. The double and the float, these are the C declarations. Single precision is float, and then double precision is double, which is 64-bit representation. But before we proceed further, just want to ask this question, that what is the difference between a floating point number and a fixed point number? So can I ask Yogesh Kumar Yadav? Yogesh, are you there?
Yes, sir. Yes, sir.
So what is the difference between a fixed point number and a floating point number?
Sir, I don't.
Okay. Okay, good. You said don't know. Now let's ask somebody who knows. Prakash Chauhan. Prakash, what is the difference between a fixed point number and a floating point number?
Sir,
Yes, yes.
sir, this is Varun. Can I answer?
Yeah, Varun. Yeah, please. Varun, yes.
Sir, sir, in a floating point, sir, the number of digits are not defined for the real part, for the integer and fraction part. But in the fixed part, fixed number, we can we have a defined number of digits for the integer part and the fraction part.
I mean, why is that? I mean, how does it matter whether you define fixed points or don't? Yes, anybody like to answer?
Sir,
So,
Yeah,
so because
yeah,
of
Varun,
that,
please. Yeah,
because
Varun,
we
please.
so because in fixed point we can define we can use like a limited range of values only, but if we want a larger range of values we can use a floating point. So like in fixed point we could have a higher performance in comparison to floating point. So like we can cover a specific for floating point we can use them in general cases, but not in case of fixed point. For higher performance we can use them in for some other cases.
Okay, so okay, it's somewhat okay, but let me just tell that in floating point representation, we shift the decimal point there to be able to do addition subtraction, which is suitable for computer. Because we can't do this addition, fixed point addition subtraction, computer does not do. We don't really add as we proceed, we'll see that. And also the precision will be higher in a floating point. Because the representation in computer, if we fix how many fractional bits will be there, that 4 or 8 or something, it will be very constraining. We'll lose precision. But here we maximize the precision. Let's proceed. But you think of it. You do a search on the net or wherever, because somebody is going to ask you this question someday, or you might ask to yourself that what is this? Because everybody is saying that floating point number and fixed point number, and what is the difference? Please do some study. Look in the net, Google search, look in the book, and you just convince yourself that why the floating point numbers are used in computers and not the fixed point numbers. And also think of the answer that I gave. Okay. Now let's look at the IEEE floating point format. So here we have one sign bit here. Depending on whether it is 0 or 1, just like in a integer, depending on the sign, we have a positive or negative floating point number, and we have a fractional part and an exponent. The exponent, out of the 32 bits, 1 bit gone on sign, 8 bits on the exponent. So that means 2 to the power 8 can be the exponent. But what about negative exponent? We don't want to do the business of storing a sign for exponent also. Right? Just see the complication here. Because exponent can be positive or negative, and we don't want to do this business of exponent again, keep a sign bit on the exponent and so on. And the fraction is 23 bits. 23 plus 8 plus 1 is 32. And similarly, for a 64-bit representation, 52 plus 11 is 63 plus 1, 64. So the exponent is 8-bit in a single precision, 11-bit for double precision, and we don't want to this business of keeping a sign bit and doing a signed addition and so on, signed subtraction and so on. So how do we proceed? Okay, the answer is that we store only positive exponent, but then we apply a bias there. So the bias is 126, 127 for a single precision number. The bias is 127. 2 to the power 8 is 256. So if it is all zeros, the exponent is all zeros, then it is a minus 127. And if it is all ones, then it is 256 minus 127. So that's the meaning of the bias. But then we'll see that all zeros and all ones on the exponent are reserved for some purpose. We'll see that. So the representation here is that the sign bit, depending on it is 0 or 1, it is a positive or negative floating point number. We represent that in minus 1 to the power s bit. So if s bit is 0, then it is a positive. But if s bit is 1, then it is negative. Now here done the IEEE floating point format done a very smart thing actually. We had observed that in the normalized representation of floating point numbers, the number on the left of the decimal of the digit, the point, decimal point here, or binary point, whatever we say here, binary point, is always 1. That's the normalized representation. We had seen that. So there is no necessity of storing a 1. If we had a number like, let's say, the one example, okay, this is the number. So we don't need to store this 1 because it will always be 1. So that's a nice smart thing the IEEE representation has done, that 1 is always there. So need not as well store 1. So we need to store only this fraction part and also the exponent part and the sign. The sign, fraction and the exponent don't have to store this 1. And while computing the result, we'll add that 1 back. And similarly, for a double precision, we have this bias is 1203. Whatever be the exponent works out to be, so that is 2 to the power 11, that is 2048, right? So on that we'll subtract this 1203. Now the exponents, this all zeros and all ones are reserved for some purpose, as I was saying. Now we'll see what purpose a little later. But before that, let's find out what is the smallest value that we can represent using a single precision IEEE 754 floating point standard. The exponent cannot be all zeros, so the smallest exponent that we can have is all zeros and 1. And if we compute its actual value, it is 1 minus 127 is minus 126. That's the exponent. And the fraction part can be all zeros, and the significand is 1. And once we reconstruct the number 1.0 into 2 to the power 1 minus 126, which is equal to either depending on the sign, it is 1.2 into 10 to the power minus 38 or minus 1.2 into 10 to the power minus 38. It's no prize to get 2 to the power minus 126 to this number, because 2 to the power 10 is 1024. So that's what we have done, it 1.2 here. And so 2 to the power 10 is 10 to the power 3. So that is 12.6 into 3. Okay, So that's how we are getting 10 to the power minus 38. It's a small manipulation, number manipulation. And the largest value on the other hand, we cannot have all ones. So we can have this as the largest exponent, which is meaningful. The other one is reserved for some purpose, which if you compute, it is 254. So the largest exponent we can have in a single precision is 127. And the largest fraction can be all ones. And if we put the significand 1.1111 and so on, it is approximately equal to 2. And therefore, the largest number that you can represent in the single precision is 2 into 2 to the power 127 is 3.4 into 10 to the power 38. Similarly, in the double precision, if you just do this small computation here, you will get 2.2 in 10 to the power minus 308 and 1.8 in 10 to the power 308. So these are the ranges that you can represent using a IEEE floating point format. But what about the precision? See, every bit in the fractional part is significant. So in a single precision, let's say the LSB is 1. Now, what is the value of that? That is approximately 2 to the power minus 23 because there are 23 bits and the LSB is 1. So the precision is 2 to the power minus 23. So that's the precision with which we can operate. But how much is this in decimal? Okay, that is equal to, if we do this log thing, so if in decimal, if it is AX, and so basically if we take log with base 10, then this will be log 2 base 10, and therefore 23 into 0.36. So the number of decimal digits, okay, it is 6-digit precision. So 0.000001, that is the number, least number we can handle in single precision. We cannot handle precision 7 zeros and 1 or something like that. If anybody has doubt, please let me know. These are simple maths. I think you should be able to do it. Very simple maths, school maths actually. And similarly for the double precision, we have 2 to the power minus 52, which is equivalent to, if we do this, how many digits we can manipulate. The list is 16 digit. So 0, 0, 0, 0, 15 zeros and 1. So that's the smallest number we can manipulate. If it is anything less than that, we have to ignore it. That will get, we will not be able to handle, or that will be made 0. We lose precision. If anything less than 15 zeros and 1, anything less than that, we cannot handle, and that will be approximated to 0 in computer arithmetic. I hope this point is clear. We are unfortunately running out of time. We'll continue from this point. The next class, Monday, we'll have a quiz on Monday. Anybody has any questions, concerns? Let's hear about that, 1 or 2 questions, and then we'll stop. Anyone wants to tell anything? Okay, so everything is fine. Then I presume.
Sir?
Yeah, please. Yeah.
Sir, in the class test,
Yes.
we are not satisfied with the marks we are getting. Like, if we are writing the same answer to the same question, 2 people are getting very different marks. And when we are
Yes, sir.
Mainak, the protocol
Correctly.
is Mainak. See,
Yes,
I understand the concern. The protocol is that the TAs are evaluating. Okay, I am not evaluating. So you fast.
Yes.
You first
I
mail them.
understand.
You first mail them. Okay, anybody has difficulty in the evaluation, first mail the TA that I am not satisfied with my answer evaluation. And if it is not satisfactorily resolved, even after you writing, you write to me. I will take care of that. Anybody who is not satisfied with the evaluation with the TAs, then you write to me. I will take care. But first time, please write to the TS and try to get it resolved with the TS. Maybe they just overlooked something or.
Yes, sir.
Okay, because they
I
have been
understand
given
that.
clear guidelines. They have been given clear guidelines how to evaluate. So non-uniformity should not happen. But in case you are not happy, please write to me. I'll take care of it.
Okay,
But
sir.
don't delay too many tests. Within one test, within a week, you please write to me. Don't tell me that in the first quiz something happened, etc. It will be difficult for me to handle. So one last quiz I can see. Okay, please write to me within 1 week. Okay.
Okay, sir.
Okay, thank you very much. We'll stop here.